turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers from the worlds of science, technology and medicine. I'm Chris Smith. This week, we've teamed up with Cambridge University Press and specifically the team behind Research Directions, their suite of new open access journals that are all about publishing research in a novel and exciting way. Science is, of course, all about asking questions and developing experiments to test hypotheses. But only rarely does a topic have a single facet. Instead, one key question invariably leads to many others, and the answers to those can, as the Research Directions team put it, assemble into chains of collaborative work. They're asking really important questions, some of which we're going to turn into podcasts that will be called Research Directions. That's on the way, and this is our first go. In each episode, we'll hear from the journal editor who's proposed a key question relevant to current research priorities. Then we'll hear from a series of authors who've heeded the call and are working on solutions that address that big question. This time, the buildings and the built environment we inhabit are what we're going to explore. So let's meet the editor.
My name is Martin Dade-Robertson. I'm Professor of Emerging Technology at Northumbria University, and I'm also the Editor-in-Chief for the Cambridge University Press journal Biotechnology Design.
You're making a very auspicious start, Martin, because this is the first of these programmes we're making. And it's very exciting because the question that you put forward, if you'd like to tell us what it is, immediately got my creative juices flowing. So tell us what the question is that you think we're going to address in this episode.
Yeah, so the question is, can we grow a building? And then there's a sort of separate bit to that question is, and would we want to?
Well, let's start with the first one then. Do you literally mean as in growing a building out of the ground? Or do you mean growing the component parts of a building?
Literally, yes, in the sense that that's the aspiration, although we have to break down that problem into smaller parts. So it does make more sense. And the way we're tackling it in the journal is to look at those parts separately. But the analogy that I give often to our group and the people that we collaborate with is a tree. So the idea that we construct in the way that a tree constructs itself, so using only the natural resources available to it in its immediate environment through the soil and so on, and then able to self-assemble a really complex structure with multiple different functions and able to survive and then maybe even live after it's been constructed. So if we think of a tree, think about a building constructed in that way, that would be the sort of the grand ambition.
It's got foundations, roots, it's got structure, which is the trunk, it's got layers, the stories, because you've got leaves, and then it's got solar power, as well as drainage and water.
Drainage and water, yeah, a whole plumbing system built in. And it does it with very little materials. So cellulose is the same stuff that's used in the trunk is used in the leaves, albeit in different mixes and organized in very complex ways. But it provides us with a sort of template for how we might think about construction in the future.
Obviously, we do use timber in the construction industry, and it's one of our oldest building materials that we as a race, species, have had access to. But what do we need to do then in order to realise the aspiration of buildings that do grow themselves, or all the component parts of buildings grow rather than get made?
Yeah, we absolutely do. So we already have the principles of using biology in our built environment. So not only trees, of course, we've also got things like limestone, which are calcified remains of sea creatures and so on. So we're used to using those materials, but we have to think about them in a slightly different way. So we usually harvest the materials after the organism that created them has died. And so we're taking what we're given and then we try and construct our buildings around what those materials will do, often by processing them quite heavily. But to think about a building as something which is grown, we need to think about the building being assembled while the organisms that is creating the building are still alive. And that involves thinking about how we interact with that biology to make materials that are suitable for human purposes, but also allow the kind of biology to do its thing.
You said in opening, would we want to do this? What would be the benefit of that? Why would we want to do it?
If we think about the tree example that I gave again, I mean, the first thing that's most often on my mind is that the tree assembles itself whilst it sequesters carbon dioxide, and that's the complete opposite of the way that we construct at the moment. So that would be a big goal if we can get to a construction process that sequesters carbon dioxide as a building is built. There are also the benefits potentially of self-assembly, so materials that can organize themselves, so we don't have to go through the heavy process of constructing and removing materials around from place to place to make. So again, the tree example is one where we're using only local resources. And then there's a sort of idea there as well that rather than having to maintain our buildings, the buildings themselves will maintain themselves. So living organisms are adaptable to their environment. They're capable of changing and responding to different conditions, things like self-healing. These are things that our buildings currently can't do. So that would be the kind of ultimate aim, if you like, of a truly sort of biological architecture, that it could do all of those things.
How close are we to being able to realise any of this? Because it sounds fantastic and you can immediately see why this is an attractive option, but it also sounds quite unrealistic in the sense that buildings work a certain way, and to live in a tree, yeah, I've heard of tree houses, but there are limits.
Yeah, there are definitely limits. And so there are lots of limits to the current technology, but some of it is a little bit closer than you might think. So just to give a couple of examples, there is already a company that makes a type of concrete, for example, that has bacteria spores, like the seed form for bacteria, embedded within the material, so that when it cracks and water gets into the cracks, the bacteria spores germinate, they come alive again, and then they produce calcium carbonate crystals to heal the material. So this is a viable option. It's a biological material and it has that capacity for self-healing. There are other examples as well. Mycelium, which is the root network of fungus, can be used to make a really good bulk material very quickly. It's often thought of as being a good acoustic or thermal insulator. So we grow that material to give us particular material properties and characteristics. At the moment, we grow it in the lab, but there are factories that grow it as well. And it creates, as I say, a really robust, often quite fireproof, mainly insulation material. So there are examples where we've got materials that are actually a little bit close to real construction that might not reveal the sort of the whole vision of a growing building, but where we can certainly grow parts of our building to really, I guess, quite tight specifications.
Recycling, though, presumably with a grown building, if nature gave it to us, nature can take it away. Now, that has a pro and a con aspect to it, because wood going mouldy and rotting is notoriously a problem, but it makes the recycling headache go away, presumably, doesn't it? Because at the moment we are discovering to our cost that we should have thought about how to recycle materials earlier in the day than we often did.
Typically, we design our buildings with a predicted 50-year lifespan. And of course, if we look into our built environment, we can find plenty of examples of buildings that have been there for 100 more years and often a lot longer, right? So what we don't want is our buildings to biodegrade at the wrong time. So this is an issue. How do we allow our buildings to be biodegradable when we want them to be? I think there's also quite a lot of work to be done in things like the way we package up building materials and move them onto site. And one of the big issues of constructional waste actually is the amount of packaging and protection that we put our building materials into. And this is particularly true in the context of off-site manufacturing of buildings, for example, where we're doing a lot more now in factories where we're making very precise building components, but they have to be protected and then moved to site. We think this is an area where biology can help as well, where we can have these materials which are much more biodegradable and therefore sustainable. They don't add waste into the environment in the same way.
Martin Dade-Robertson, Editor-in-Chief for Biotechnology Design, asking the question, can we grow a building, and would we even want to? So now let's meet the researchers working in some of the sectors that Martin identified. Later, we'll explore how to manipulate the microbiome of the built environment for optimum health. But first, let's stick with the microbial world, but hear how it can give us raw materials to work with.
My name is Jonathan Desialov. I'm an assistant professor at the University of North Carolina at Charlotte, and I teach courses on building structures and biomaterials. We have built buildings with kind of the same materials for a really long time. And what we're starting to see is that while some of those materials have done us well historically, they have lasted a very, very long time, nearing permanence. We're also starting to see that as we start to make composites, so as we start to bring multiple materials together, sometimes we bring them together in ways that are not reversible. And so what we're doing in my lab is looking at how we can start to partner with new materials, materials that can be cultivated, materials that can be manufactured, but rather than using petroleum or high energy processes, that we can use quiet, sustainable organic growth.
What sorts of materials are these?
My particular focus with these sorts of new biological materials are the use of fungus, more specifically mycelium, which is the root part of the fungus. So under the ground, mostly invisible to us, is a intertwined, interweaving network of these literal tendrils, and they weave together like a web, and they're the ones that are actually doing all of the work of the fungus under the ground. And so what we're trying to do is use that root structure of the fungus as basically a self-forming glue. We get the fungus to start to grow, so we have wood chips, we introduce a mushroom, and then we grow that mushroom through those cellulosic fibers until we have a sort of solid mass. So the fungus is really acting as a glue to hold together these wood chips or these cellulose fibers.
What's doing the gluing, though?
Oh, so the gluing is actually being done by the fungus. So the fungus, as it starts to cultivate, it grows onto and through the cellulose. The cellulose is both.
So in other words, the fungus is almost like liquefying or releasing, liberating components of the thing it's growing through, but as it does so, they become sticky and bind together.
That's right. It binds together everything that it grows through.
And do this presumably to the extent the fungus gets as far as binding stuff together, but then you presumably have to stop the process before it degrades the material too far, because you're going to peak at some point in terms of strength, and then the integrity is going to start to fall apart.
That's absolutely right. It's a very controlled process. So on the front end, we have to be very conscious and very deliberate about the environment that we're providing for this fungus to grow. It needs warmth, it needs humidity, it needs proper access to its food. It needs a very, very clean environment that whole time. And mycelium itself, so these little root-like fibers, they like it to be quite dark. On the other end of it, like you say, you have to stop the growth. Otherwise, it would deplete its food source and you would end up with a sort of gooey mess.
Presumably, you've got to kill the fungus.
Yeah, through heat. So for very small objects, we can put them into an oven, so a conventional oven like you might find in your kitchen. And at about 80 degrees Celsius, you can then put an object into that oven and essentially bake it dry. And that will completely stop the growth of the fungus.
What sorts of things can you make with this?
Well, we make all sorts of things. At the sort of product scale, one could imagine things like acoustical panels or cushions, or there's a company in Italy that is also making sort of floor tiles that resemble cork. At the big scale, we're thinking about growing buildings, or at least building components. And in my lab, we've grown everything from just that, an acoustical panel all the way up to a small pavilion for a barbershop quartet.
Does this meet our kind of aspiration? You started by saying that one of the big worries here with modern construction techniques is we've made some wonderful materials until the day you want to recycle them. Does this solve that problem? As in, can we literally dismantle one of your pavilions and grind it up and scatter that to the four winds and it's made no impact on the earth whatsoever?
Well, that's certainly my hope. And I think that's what makes mycelium materials so exciting for me. When we talk about buildings and design, though, we think that permanence is something that makes whatever that thing is important. And this material being something that, like you say, it could just simply get dismantled is, I think, both really romantic and exciting.
Traditional building materials we understand very well. As you pointed out earlier, we've been working with some of them for thousands of years, literally. So we understand their strengths, their weaknesses, and their constraints. What do the properties of these new materials look like? Are they any good?
From a structural standpoint, these are not stone. These are not brick. They're not concrete. They're not even wood. They resemble styrofoam, to be quite honest. So they are good at certain things. What we are making with these materials is maybe not what they are best at. And I think that's what we as humans working with this biological partner now have to try to find out. And because it doesn't talk back, we just have to continue experimenting with where are they going to perform best in our lives.
The thing that's going to be the absolute arbiter in the future is going to be climate change in terms of whether we do something or not, because I think it's going to become harder and harder to convince people that something should happen if you can't say it's got good carbon credentials. So I get what you're saying, that we have in the past viewed buildings as very much a permanent thing, and it's a success story if it's like the pyramids and still here 5,000 years later, and that this could be 5 minutes. But it's all going to come down to the energy equation, isn't it? So it sounds good, something that will last 5 minutes and then won't cause any pollution. But if it's caused a whole lot of carbon cost in making it, getting it to site, erecting it, then it's no better than if you had actually produced a whole lot of concrete.
The truth is that forever has shown historically to mean something more like 40, 50, 60 years. And so, yeah, there's those energy costs up front, but then there's also maintenance costs over the lifetime of the building. And so those energy measures, I think, are going to be, well, they're increasingly complex because, like you say, there's an immense amount of energy that would go into this at an industrial scale to keep an environment warm and humid and clean costs a lot. To dry objects that are made of mycelium materials and dry them at large scale costs a lot. It doesn't actually cost as much, let's say, as manufacturing insulation foam. The bottom line is going to be sustainability and how we can justify it, but in some cases, those measures may not be convincing enough. At least in the United States, there's certainly the perception that demolition is not only cheaper financially, but is just easier. And in some ways, that's going to be a limit, whether or not it makes sense to demolish a building and put up another one, and all of the energy associated with that. At some point, we may just decide, well, that's not really what we want to do. For me, the limitation is less about, can we do it? It's, will we want to?
Jonathan Desi-Olive there, talking about pressing wood chips into the right shape and gluing them together with a fungus. As he said, he can even make a bandstand. Now, another class of microbe may also prove to be very useful in this space. Bacteria, with the chemical ability to calcify an organic paper or wooden template, can potentially be used to make very tough and resilient structures, ranging from furniture items, very handy when it comes to actually furnishing the house we're seeking to grow, right through to the fabric of the building itself.
My name is Aurélie Mossé. I'm a textile designer by background and currently working as a design-led researcher in École des Arts Décoratifs in Paris, a school of art and design, where I lead one of the research groups called Soft Matters. So in our group, we are interested as the overall question to understand how new materials, new technologies, or maybe some of them that we have forgotten for a long time, can be helpful to design a more sustainable future. And one of the things we look at more specifically is really to see how biological process, our living organisms, can help us craft things in a more sustainable way.
What sorts of materials do you have in mind?
We work with mainly soft materials, which means fabrics or paper, but we also use the term soft to actually talk about materials that engage a chemistry which is soft, so that does not impact the environment and organisms that lives within it.
Obviously, buildings need tough materials to make them strong. So if you're just working with things that are soft and flimsy like paper, they may not be ideal under all circumstances. So what are you trying to do to come up with materials that might better fit that purpose?
So we work with a process that is possible thanks to bacteria. We call it biocalcification, and the idea is to make soft materials harder, stronger. And this is because the organism is producing mineral that is applied to the soft materials and give it a shell or a stronger aspect.
So you could take something that's like a paper mold and then make something that's much stronger on top of it.
Basically, we place the living organism on the material and we give him specific ingredients to create a chemical reaction, and then he releases the mineral onto and within the soft material and the paper in our case.
So what sorts of minerals could you deposit in this way then?
So we work with a specific bacteria, which is a calcifying bacteria, and in our case, or its case, is just producing calcite, which is a source of calcium, which is present very widely in nature, and is also renewable.
Not dissimilar really to bone or the kinds of shells that shellfish put round themselves then.
Yes, exactly. We have that in our body, in our bones, in our teeth, and we find it very commonly in different places in nature.
In essence, then, you could have a bone house. You could have a paper set of walls, impregnate them with these microbes, feed them appropriately, and they would lay down calcium.
Yes, as long as they are happy to grow on the material and you give them enough ingredients, yes, it works. We know it works well on any sort of cellulose-based ingredients, I would say, or materials.
Cellulose being obviously one component of wood, so you could literally start with paper and build a sort of model of the surface you want to calcify, and then presumably get the bacteria growing on there, and they would produce almost like a coating that was the calcium, the hard surface.
So it's not only a coating, but also gets inside the material, so it can really be structural. But it's probably easier to grow the material that you want at the scale of a brick or a furniture than at the scale of the whole building, because it means you will need to control or help bacteria to grow on a very large surface.
I was going to follow up and say, well, how big can we go with this? Because obviously there are a number of dimensions to consider. There's not just the X and Y, how like a piece of A4 or a piece of A3 paper. There's the Z dimension, the how high and how thick as well. So talk us through how this actually works practically.
So in our case, we grow the bacteria on a paper form, and we work at a relatively small scale because it's a new process or a new material that we have developed. But we know engineers that are working with the same bacteria, and they rigidify or stabilize soils at a much bigger scale. So it's not crazy to think that we could upscale the process at a much larger scale. We hope in 2 years' time that maybe we can demonstrate that we can grow a chair or maybe the frame of a window, for instance. It requires a bit of development. And in our case, the challenge is that you need to inject or to expose material and the bacteria to a certain amount of water. So the bigger the elements you want to calcify or rigidify, the bigger the water container for it. So you probably don't want to do that at the scale of the building, and therefore things more like bricks or modular components.
Aurélie Mosset there. Now, we've heard so far about the use of fungi to glue together building materials like wood to make bricks and other structures, and we've just heard how bacteria can calcify organic templates made from things like paper to produce a strong and durable structure for use both inside and outside. In both cases, though, once the microbes have done their jobs, they largely become inactive. But there's also an important ongoing living microbial relationship that we've not even considered yet, which is the microbiome. This is the assemblage of microbes that live on us and in us. And not just us. The environment has its own microbiome, the composition of which, it turns out, is absolutely crucial for our and everyone else's good health, and we ignore it at our peril. It's what Phoebe Mankiewicz from Yale University and Elizabeth Henaf from New York University are interested in studying, to discover how we can engineer the grown buildings of the future to grow the right sorts of microbial colonizers. Elizabeth first.
Well, the diversity of a microbiome is going to be related to the diversity of the ecosystem that it's part of. So a diverse ecosystem, like a forest, for example, that has a bunch of different plant species and animal species and insect species inhabiting that forest, is also going to have a bunch of different types of microorganisms that are related to all of those like visible organisms that we might be able to identify in that environment. And so in a built environment, we don't have as diverse of an ecosystem. We see more buildings than we see trees. And so because the kind of large scale ecosystem that we might be able to identify just looking around us is less diverse, then also the microorganisms are also less diverse. So the purpose of this work was kind of guided by this question about how can we make a building actually feel like a forest?
Phoebe, how are you going about this? What's the best way to tackle this? To work out what is there to start with, but then also work out how different interventions we can bring to bear will actually result in or translate into a change in the microbiome of the environment we inhabit?
So I think there's two parts to your question. Is one, how do we even look at microbiomes indoors? And that's a very particular question. And the second is, how might we change the microbiome indoors? So how are we collecting and studying the microbiome indoors? We used a swab collection. So that way we can say, what kinds of DNA are on my desk? Where did that DNA come from? Could it be this microbe or that microbe? And what might those microbes be doing in the space? Could they be breaking down air pollutants, for example? And so the second part of your question of how do we change the microbiome within a space, in this paper, what we did was we designed these sort of living machines that we often call green walls. And these have been around since the 1960s with NASA researchers. But the question is, if we pull air through plants and all of the microorganisms that live on plants, on their leaves and in their root system, can those machines improve indoor air quality? The microbiome question is, will the microorganisms in the root systems actually metabolize pollutants? And secondary to that, will the microorganisms in the root systems diversify the space in the environment that you put them in? So if it's on your desk, maybe it'll diversify your desk. And could that improve our own microbiome diversity and our own health long term?
And do they, Phoebe?
The short answer is they could. What we found was the 3 different growth media that we tried out in these living machines all have very diverse microbiomes, so they probably could benefit our health long term if we could inoculate the space around us. And they all have very different metabolic profiles. So what our research shows is that the different growth media are probably going to be good at different things. And so that's really interesting moving forward, because if you know something about the space, maybe your office has a 3D printer in it and you really want to metabolize this particular set of compounds, maybe there's a growth media that will support microorganisms that would be really good at metabolizing that pollutant particularly.
Are there then 2 aspects to this, in the sense that we could build things from the get-go and do that with this in mind, making the ideal microbiome thrive there? But actually most of human endeavour has been building stuff hitherto. Therefore we are handed an enormous legacy, and it's got its microbial and microbiomic problems. And this is presumably then more a problem of retrofitting rather than de novo design.
Absolutely. Yeah, so when people think of the question, can you grow a building, which was what was posed by Research Directions, many might assume that this is what they mean is structural. And so the classic example of a structural grown architecture are the living bridges in Bangladesh, which are beautiful living architecture made of ficus trees. But of course, that takes quite a long time. And as you said, all of our buildings are already built right now. We are building new ones, but is there something we can do with what we already have? And so that's a big part of the question that we were asking is, could we grow beneficial plants and microbes in a way within indoor spaces that already exist that could change the air quality and the microbiome of our offices or living spaces that could improve our health long term? And the short answer is yes. And secondary to that is these living green walls, these living machines, many of them already exist as well. And so are there retrofits we could do to them that would make them work better over time as we gather new information about microbiomes and how they work?
How long then, and this is to both of you, but maybe we'll start with Elizabeth, before developers are submitting a planning application, the planners are saying, right, where is your impact assessment for the microbiome of the building you seek to construct? Are we there yet, or is that coming?
We're not there yet, but I think it's certainly coming. I'm really excited to be able to hopefully see that happen in my lifetime as a scientist. There's a couple of hurdles to implementing microbial metrics in building code. And namely, we don't really have a good predictive structure to understand what the resident microbiome would be of a building given how it's built. So given the materials that are being used, the ventilation system that's being implemented. But as a field, we're accumulating a lot of information to be able to build that kind of predictive model. So understanding, for example, for different types of building materials, what is the resident microbiome that would be able to settle on that building material and thrive there. And so we don't have quite yet like a Rhino plugin. Rhino is the software that architects use to model buildings and to model all sorts of other factors that are important for building structures. But I think that that's not too far away. And once we are able to do that kind of predictive modeling, then we can start to think about how these metrics would be incorporated into code.
Phoebe?
On top of that, we also don't yet know how a particular microbiome might impact human health outcomes long term. There are very few studies, although there are now studies. When I first started my PhD, there weren't any causal studies on this in humans. And now there are, where we can change the microbiome of a place and then have measurable impacts to human health. So it's two things. One is, how will the way we build our buildings impact the microbiome of that building in that place? And the second is, how would the microbiome of that building in that place influence human health of the humans that are inhabiting those spaces? Those are two different questions, and they're both being researched, but you need both of them to be able to then have policy to say, you need to have these kinds of buildings in order to improve human health in cities.
Phoebe Mankiewicz and Elizabeth Hennef there on why growing a building isn't just about the stuff we can see. The day is coming when we're going to need to plan an impact assessment for a building's microbiome as well. So have we convinced you that Martin's question of whether we want to grow a building is a realistic prospect? I must admit that I had no idea the field had come so far and so fast before I embarked on this programme. But perhaps the most important person to ask is Martin Dade Robertson himself.
Well, I think we can tell from your interviews the huge diversity of different approaches and technologies that there is no single or simple answer to the question of whether we can grow a building. And that's one of the things that's really exciting about this kind of question-led approach to research. It doesn't preclude different voices and different disciplines getting involved in the conversation. I guess the other thing that struck me in listening to those interviews is whilst there is huge diversity there is also a shared sense of mission, I think. And so whether we can grow a building in the next 10 or 20 years' time, I think this idea that we're working with technologies that are more attuned to and have a better understanding of the natural biological world around us, even when we're using it for our own purposes, is something that we need to think about across a whole range of different technologies in the future, a kind of different way of thinking about the way we build in our environment, actually. And I think that that's a kind of emerging theme of this question and indeed the journal overall.
Thanks, Martin. So what do you make of the concept behind research directions? Your thoughts and feedback are extremely welcome. Please get in touch. It's chris@thenakedscientist.com. That's it for this week. Do join us next time for From Russia with Love. No, we're not ripping off a James Bond. We'll be asking how Russia's using science and technology to undermine the West. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the Naked Scientist team, thank you for listening, and until next time, goodbye.